Now that we've talked a little bit about what logarithms represent, let's talk about logarithmic functions. If we have f of x equals logarithm base a of x, where a is greater than 1, then the graph of this function will look somewhat like what we see here in the first box. What we see is a graph that has a vertical asymptote at the y-axis, which is the x equals 0 line. So the graph will approach the x-axis as it travels to the left, and it'll grow without bound as we move to the right. There are some key points that will help guide what this graph looks like for you. The point 1, 0 will be an x-intercept. You'll have an additional point at a, 1. We'll see why this makes sense as we build a table of values. We also have a point at 1 over a, negative 1. If you can graph these 3 points as your guide and remember about that vertical asymptote, that should be enough for you to get the basic shape of your graph. On the other hand, if we have f of x equals logarithm base a of x, where a is still positive but less than 1, so think about values of a like 1/2 or 1/3, then we will have a graph that is decreasing over its entire domain. You'll still have a vertical asymptote at the y-axis at the x equals 0 line, and you'll still have the same 3 guiding points, but because the value of a is a proper fraction or a quantity between 0 and 1, the a over 1 point and the 1 over a, negative 1 point will be different. Let's take a look at some examples. In fact, we're going to use a parent function, and then we're going to use a transformation to show you that transformations are also possible with these types of graphs. Now, it's important to note before we dive into the example we have here that logarithmic functions and exponential functions are inverses of each other. Because they're inverses of each other, think about what we did in chapter 3 with inverse functions. Basically, x and y switch roles. So it makes sense that when it comes to the domain and the range of logarithmic functions, these are the reverse of the domain and range for exponential functions. So for exponential functions, the domain was always a set of all real numbers. Well, that will be true for the range of logarithmic functions. For exponential functions, the range was from 0 to infinity with 0 not included. Well, here, that will be the case for the domain. So basically, what we knew about x and what we knew about y is now flip-flopped. All right, let's take a look at our first logarithmic function. So we have f of x is equal to logarithm base 3 of x. We already said that this is going to have a vertical asymptote at the y-axis. So I'm going to go ahead and add that as a dashed line for guidance. Then we have 3 guiding points that we know are part of the graph. Here, our base a is 3. So we have 3 guiding points, 1, 0, a, 1, and 1 over a, negative 1. So for this graph, obviously 1, 0 is pretty straightforward. A, 1 will be 3, 1, which should make sense. Basically, it's asking, what is the logarithm base 3 of 3? Well, 1, because 3 to the first power is 3. Similarly, if we have 1/3 for x, then y is equal to the exponent on a base of 3. That would give us a result of 1/3. Well, 3 to the negative 1 power will give us 1/3. So that'll give us our third guiding point. So now if we plot these 3 points on our graph, we have 1, 0, 3, 1, and 1/3, negative 1, right about there. That's enough for us to estimate what the rest of the graph will look like. Now this is the overall shape for all logarithmic functions. In fact, you'll see that if you apply what we learned at the end of Chapter 3 about inverse functions, reflecting this graph over the y equals x line will give us the graph of f of x equals 3 to the x power. In other words, the exponential function with a base of 3. Now let's take this parent graph and apply a transformation. In the next example, we have f of x is equal to the logarithm base 3 of x minus 5. So it's the same parent function that we just graphed, except here I see that we will need to move the graph to the right 5 units. That also means that the vertical asymptote will move to the right 5 units. So let's go ahead and add that as a guide. Basically, the 3 points that we had in our table of values earlier will need to move over to the right 5 units. So we're going to add 5 to the x-coordinates. Here we have 1 for x. Once we add 5, we'll get 6. So 6, 0 will be one of the points on the new graph. Then we had an x-coordinate of 3. We're going to add 5, so we get 8, 1 as another point. And our third x-coordinate in the parent graph was 1/3. We're going to add 5, so we have 5 1/3, comma, -1. So let's go ahead and plot these points, 6, 0, 8, 1, and 5 1/3, comma, -1. And again, that's enough for us to predict what the rest of the graph will look like. Now let's go ahead and find the domain and the range for these two graphs, for these two functions. Notice that in example 1 here, our domain is restricted. We have a vertical asymptote at x equals 0, and the graph will continue traveling to the right without bound. The range, however, is unrestricted, so the range will cover all real numbers. In the second function, the one that we translated 5 units to the right, the domain is restricted. We have a vertical asymptote at x equals 5, so the domain will go from 5 to infinity. The range, however, is unrestricted, and so it'll be all real numbers. In the next few examples, we are going to look at the domain of given functions. And to be able to find the domain, recall that the argument must be positive, must be greater than 0. So for the function f of x equals logarithm base 5 of -3 minus 7x, we'll have to set -3 minus 7x to be strictly greater than 0, which means that the opposite of 7x must be greater than 3. Dividing both sides by -7 will give us x on the left and -3/7 on the right. However, because we're dividing by a negative number, the direction of the inequality will reverse. So we can write the domain in interval form as having no lower limit, so going from -infinity up to and not including -3/7. Next, we have f of x equals natural logarithm of 7x minus 28. Recall that the natural logarithm has a base of e. In this case, however, we just want to set the argument to be greater than 0. We'll add 28 to both sides, so we get 7x is greater than 28. Dividing both sides by +7 gives us that x must be strictly greater than 4. The domain in this case will go from 4 to infinity with 4 not included.